Welcome. In this video, I'll be looking at the graphical analysis of satellite orbits. In particular, we'll be looking at the context of energy changes. So we have here a visual of a spacecraft, Juno, that was launched in 2011. And it today orbits Jupiter. It was one that was launched by NASA. So let's have a look at the following video to get some background on the NASA satellite called Juno.
After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year.
So the scenario we have for our problems is as follows. So the spacecraft Juno was launched 2011, yes, around orbit of Jupiter. So the table we have here shows us information about the planet Jupiter and the spacecraft Juno. So we have the mass of Jupiter, the radius of Jupiter, the planet, and the mass of the spacecraft Juno. The graph below shows the gravitational field strength on the vertical axis plotted against the radius, or the distance from the center of Jupiter, in units of by 10 to the 8 meters. So let's consider a couple of questions. So question number one, we want to calculate the gravitational force acting on Juno by Jupiter when Juno is at a distance of 2 by 10 to the 8 meters from the center of Jupiter. Okay, so let's have a look. Here on our graph is 2 by 10 to the 8 meters. So at this radius of 2 by 10 to the 8 meters, we find there is a gravitational field strength of 3 newtons per kilogram. Two ways of solving this problem. First of all, to find the force on Juno as a result of the gravitational strength of planet Jupiter, we could simply take our field strength of 3 newtons for every kilogram and multiply it by the number of kilograms in the satellite. So F equals m times g. 1500 times 3 gives me 4,500 newtons, or 4.5 by 10 to the 3 newtons. This is the preferred option for answering this particular question, because if you're given a graph, as we were in this question in 2018 from VCAA, you're expected to use it. Option number two, some students would have chosen to use Newton's equation for gravitation. So we want to find the force. We know the mass of the planet, we know the mass of the satellite, we know the universal gravitational constant, and we know the radius of separation of the two bodies. So with that information, we could use the equation that Newton created, sub in our values for the universal gravitational constant, the large mass, capital M, for the larger of the mass, Jupiter's mass, little m for the satellite's mass, and divided by the radius between the two center of the bodies squared. And in doing that, we end up with a value of 4.75 by 10 to the 3 newtons. Now, this is a little bit larger than the 4,500 newtons we got using the graphical technique. However, it's using information available from the VCAA datasheet. So examiners would probably be forced to give marks for this as well. Again, I'd encourage students to use the graph if a graph has been given. Second question. As the satellite moves from a radius of 2 by 10 to the 8 meters into a smaller radius of 1 by 10 to the 8, halfway, or dividing it by 2, we want to find out what is the change in gravitational energy. It says the word estimate, which means there's going to be some room or scope for different answers. So we're starting here at a radius originally of 2 by 10 to the 8 meters. As that satellite moves in, we're now moving to a radius of only 1 by 10 to the 8. A little bit of a quick recap. Okay, first of all, let's have a look at the inverse square law. We know that as a satellite is sitting here at the radius of Jupiter, if we allow that to move out to double the radius, what we find is the force on the surface is now only 1/4 of what it originally was. Same with the gravitational field strength. The original gravitational field strength of the surface is now at double the radius. Okay, one radius is from the center of the planet Jupiter to its surface. Double the radius takes it out to double the radius is now 1/4 as well. This is because of the inverse square law. We can see here that the force is proportional to 1 on r squared, and the gravitational field strength is also proportional to 1 on r squared, exactly the same shape graphs. Okay. It's worth noting also that if we were to somehow move our satellite into the center of the Earth, it has a linear reduction of force down to 0 at the center, and also a linear reduction relationship in gravitational field strength right down to the center. At the center of the Earth, there's force coming in from the rest of the mass, but they all cancel out to give you a value of 0. So let's have a look. If I've doubled the radius, my r is a factor of times 2. When I square that, I get now a force of 1/4. That is the inverse squared law. Here again, my radius is increased by a factor of 2. When I square that, I get a gravitational field strength is now 1/4 of the original value. Let's repeat that now when we triple it. See the same thing. If I triple the radius, I now get 1/9 the force. And if I triple the radius on this side as well, I now get 1/9 of the gravitational field strength that there was at the surface. Exactly the same relationship as last time. Factor of 3 gives me 1/3 squared, 1/9. Factor of 3, 1/3 squared gives you 1/9. That's our revision of the inverse squared law. Let's have a look now at what happens in terms of area. If we double our our radius rather, we find we have this area underneath the graph. Same with the gravitational field strength. These are two separate graphs. This one is force times radius. This is gravitational field strength times radius. When we double the radius, we get this area under the graph. Let's see if we can make some sense of that. So first of all, the area under a force radius graph gives you the work done or the change in energy in joules. Check the units. Force is measured in newtons, radius is measured in meters. Join them together. 1 Newton meter is in fact 1 joule. On the right hand side here, the area under a gravitational field strength radius, not force, but gravitational field strength, is equal again to the work done per kilogram of the satellite. So here we find gravity is measured in newtons per kilogram, multiplying by a radius of meters. So a Newton meter is a joule, but it's multiplied by per kilogram. So this is the amount of energy per kilogram of the satellite. So work done is equal to the change in energy. As we move this satellite out, some radius has been work done on the system, probably by firing jets or something like that. So as the radius increases, we gain gravitational potential energy, but we lose kinetic, so the satellite will slow down in a larger orbit or radius. Alternatively, if we move in closer, as we reduce the radius, our gravitational potential energy is reduced and our kinetic energy increases, which means smaller or shorter orbits produce rather a higher velocity. Let's have a look now at tripling. Exactly the same thing. As we triple our radius, we get a larger area, greater change in energy. As we triple our radius, the gravitational field strength also gives us the same area underneath. Again, this first graph provides us with the work done or the change in energy. This second graph provides us with the work done or the change in energy per kilogram of the satellite. Let's try this now. So question 2 again was to calculate the change in energy as Juno moves from 2 by 10 to the 8 meter radius, halving that to a 1 by 10 to the 8 meter radius. Here's our area. Let's work out the area under this graph. First of all, let's count the yellow rectangles. I call them squares, but I suppose they really are rectangles. There's 9 in total. Then, if I consider this combination of red rectangles, half of it's being counted. You can see that shape's almost exactly the same, if not exactly the same as the white space. So that's half the red squares, plus again, half of the blue squares. So there was 9 yellow, half of the 3 is 1.5 of the red, half of the 7 is 3.5. When you add them together, that's a total of 14 squares. Okay, let's work out the area of 1 square. 1 square is 1 unit high and 0.5 by 10 to the 8 wide. If I multiply them together, that gives me 0.5 by 10 to the 8 Newton meter per kilogram or joules per kilogram. This was gravitational field strength against radius. So the area underneath this graph will be joules per kilogram. So there's that many joules per kilogram for every square. And we know, of course, 14 squares by that amount. 14 by 0.5 by 10 to the 8 gives me a total of 7 by 10 to the 8 joules for every kilogram of matter the satellite has. So the final step is to multiply 7 by 10 to the 8 by indeed the mass of the satellite, which is 1500. Gives a total answer of 1.05 by 10 to the 12 joules. Okay, so the change in gravitational potential energy as Juno moves from 2 by 10 to the 8 meter radius into half of that, 1 by 10 to the 8 meters radius, is 1.05 by 10 to the 12 joules. Okay, our third and final question. Europa is a moon on Jupiter. It has a circular orbit of 6.7 by 10 to the 8 meters around Jupiter. calculate the period of Europa's orbit. So we have t, the period equals question mark, r, the radius of separation of 6.7 by 10 to the 8 meters, capital M, the mass of the larger object, which is Jupiter, is 1.9 by 10 to the 27 kilograms, and of course G, the universal gravitational constant, has a value of 6.67 by 10 to the negative 11. The equation we're going to choose is gm over r squared equals 4 pi squared r over t squared, one of the equations we have for acceleration of planetary and satellite bodies. So at the moment we want to find t. T is on the bottom on the right hand side, it's the denominator. I want to make it the numerator. It's much easier to deal with if the unknown is on the top of the fraction. So because I've got two fractions that are equal, I can effectively flip or invert both sides. Now I've got the t squared on the top, I've done the reverse, top and bottom switch on the right, top and bottom switch on the left, and that can only happen with two equal fractions like this. I want to find t by itself, so to do that, at the moment it's divided by 4 pi squared r. I multiply that across and then take the square root to get rid of the squared. So here's my expression for t. The period of Europa will be the square root of 4 pi squared r cubed over gm. All we have to do now is sub in our values. I've color-coded them so they're a bit easier to follow. So our equation here, let's substitute in the radius, 6.7 by 10 to the 8 cubed, substitute in the universal gravitational constant, and of course the mass, big M, of Jupiter, not Europa. We don't even have the mass of Europa in our data. Big M being the big object, which is Jupiter, 1.9 by 10 to the 27. Sub in those values, do our calculations, and we find the answer for the period of Europa around the planet Jupiter is 3.06 by 10 to the 5 seconds. Look, I hope this video's helped you visualize and try and come to terms with how areas under graphs can be used to calculate the change of energy or the work done in a satellite around a central body or a planet. Okay, remembering when we move further out in our orbit satellite, we increase the gravitational potential energy and we decrease the kinetic energy. However, if we're moving the orbit to a smaller or shorter value, moving it in towards the planet, we increase our kinetic energy and our speed, and we reduce our gravitational potential energy. Now, as always, if you've enjoyed this video and it's helped you understand some concepts, please remember to like, share, and comment, and don't forget to subscribe. Thank you for watching.